Modes of speciation. How does speciation happen? There's two main models, the allopatric one and the sympatric one. Allopatric speciation is speciation due to the geographic isolation of populations. So let's say we have populations A and B that are geographically isolated. Well, what can happen in population A? Microevolution, right? Drift, selection, whatever. Well, same thing. Microevolution can happen in population B. Selection, drift, whatever. The point is, they're undergoing microevolution completely independently of each other, and as that happens, they become more and more genetically different, such that if they do come back together, they are no longer freely infertile. Some reproductive isolation mechanism has formed. There are lots of examples of this in nature. It's also been directly observed, but because it is geographic, biogeography is a very powerful indicator. The species of finchbirds on the Galapagos Islands, the separation of sister species of snapping shrimp across the Isthmus of Panama. All kinds of examples of allopatric speciation. Sympatric speciation is speciation without geographic isolation. Well, how can that happen? Well, there's several ways. Well, strong disruptive selection. In a previous video, I mentioned that disruptive selection selects against both extremes against the intermediates, possibly being strong enough to separate them completely. This is in progress with the apple maggot fly and the hawthorn fly since the introduction of the apple tree. Polyploidy is pretty common in plants. This is when plants have a doubling of chromosome number, and if the plant with the doubled chromosome number is able to survive and reproduce with itself, then you have essentially a new species that is already reproductively isolated from its parent. Now, there's different ways that polyploidy can do this. Autopolyploidy is self-polyploidy. That is when you simply have a doubling of the chromosome number. But allopolyploidy can happen when two different plants hybridize to produce a sterile hybrid, and then it doubles its chromosomes to have an even number of chromosomes to be fertile again. That's what happened with breadwheat. Strong sexual selection is what is believed to have led to the sympatric speciation of all of those African cichlid fish in the Rift Lakes in Africa. So those are forms of sympatric speciation. Now, when it comes to evolutionary rates, there is no one-size-fits-all approach. Adaptive radiation is a term which describes the relatively rapid production of lots of species. Oceanic islands show a lot of diversification because of allopatric speciation. Strong sexual selection in African cichlids, also a case of adaptive radiation. So adaptive radiation can be both allopatric and sympatric. Now, what about evolutionary rates across time? See, Darwin was doing good with natural selection, common descent, and so forth. But he also postulated that evolutionary rates across time should be slow, steady, gradual, and constant. But there's a problem with that. Actually, there's two problems with that. Number one, there's no basis to assume that. And number two, the fossil record doesn't show it. It shows jumpy, 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 jumpy. So that view of gradualism has simply been replaced, largely abandoned, and replaced by the newer concept of punctuated equilibrium, which describes a non-constancy of evolutionary rates across time. So you may have fairly long periods of time with a status quo in the environment, not a whole lot of change going on. But then there's an upset or a change in the status quo, and that can lead to rather rapid evolution in a fairly short amount of time. This can describe mass extinction events followed by adaptive radiation of the survivors.